Okay. Good afternoon, everyone. Welcome to this session on quantum communication. We have an exciting lineup of invited speakers, so I'll try to keep this introduction brief. My name is Kabat Hishami. I'm a research officer at the National Research Council of Canada, an adjunct professor at the University of Ottawa and University of Calgary. It is my pleasure to be chairing this session on quantum communications. Our first speaker is Professor Li Jian. She's a professor at the Department of Electrical Engineering and Electrical and Computer Engineering at the University of Toronto. She started her work with on photonic devices for high-speed optical communications. And since she joined the University of Toronto, she's developed the technology for quantum key distribution and quantum communications. She has done pioneering work on decoy state quantum key distribution, quantum random number generation, measurement device independent quantum key distribution, and most recently, twin field quantum key distribution. And today she'll be talking about practical long distance quantum communication based on twin field quantum key distribution. Please join me in welcome Professor Jian.
Thank you very much, Dr. Hashimi. It's really my great pleasure to be here, and thank you for the invitation. Yeah, so I'm here. I'm coming from an engineering background, so I'm going to talk about quantum key distribution and talk about sort of the progress of quantum key distribution in terms of technology and about our own recent work. So, as you know, data communication security is very important. We deal with it every day. We need it every day, and it's more so during this COVID time. So I don't have to say too much about it. Now, is QKD the answer? So that's the question on many people's mind, not just ordinary people, but on the government and decision makers' mind. And I have been asked this question that will QKD become a commercial technology? Will it be widely used? Every time we have a student graduate, that's sometimes a question from the committee. So I have two answers. The optimistic answer, of course, is that there are already companies that are commercializing QKD, and they make commercial products, and they in fact have trials and so on. And there are a growing number of these. There's more and more. If 2 years ago, it hasn't been that many companies. Now I don't even have the space to put all of their logos in. I just select some. But I also have a cautious answer, which says that QKD can be a commercial technology only if it can offer it can be offered at a competitive cost over reasonable distances with sufficiently high key rates, while still providing a level of security that is more costly to break than the alternatives. So this is a tall order if you really think about it, right? And I'm going to first review the progress of QKD from its genesis BB84 in 1984 to today. And I have very short time to do that. So here's a brief outline. I'm going to review the progress in a very broad stroke, and then talk more about our recent work in twin field QKD. And there goes. So 1984, Charles Bennett from IBM and Gilles Bessart, Canadian here, invented the BB84 protocol, and that started the whole quantum cryptography field. And you probably are all familiar with this. So Allison sent a quantum state to Bob. Of course, that is the idea. It's idealized, and really you need, according to this protocol as it was presented, you need ideal single photon source, you need ideal detectors, ideal channels, basically. So it's a bit of fairy tale, right? Everything is idealized, and you need Alice and Bob, and basically they're saints. But now let's look at what we are interested in. So I'm going to talk about this relationship between the key rate and the distance, because that's, after all, those are the two key things we're interested in communication, right? On top of it, there's the security. But you need all three. You need key rate, distance, security, and you need practicality, right? Cost. So these are all important things. Now, if you think about BB84, Alice sends a photon to Bob. That photon has to arrive there. So automatically you have this negative slope 1 relationship between your key rate and the channel transmittance, which translate into distance, right? And the slope of -1 is because if your channel has 10 dB more loss, then there's only 10% of the photons will arrive, and that's why you have a slope of -1. And in 2000, there's Presco's work to prove, actually rigorously to prove the security of BB84 protocol. And that retains that slope of -1, but it still requires single photon sources. And as we know, even up until today, there is no ideal single photon sources out there. So, so the next thing is to make QKD more practical. One say, well, okay, we can dispense with single photon sources. We can use weak laser sources, which is coherent, weak coherent pulses. But then there is what's known the attack of photon number splitting attack. Eve can play tricks, taking advantage of occasionally you have multi-photon pulses. And to reduce that probability, you really have to reduce the average photon numbers of the pulses that Alice sent to Bob. And then it turns out the higher the channel loss, the lower the average photon number that you can send and still make it secure. So the bad news is that now the slope is worse, is -2 rather than -1. The good news, of course, is now you don't have to use single photon sources. So this is the major contribution. They also talk about some other practical issues that one can correct errors, misalignment, and so on in this GLLP paper is a major milestone as well. So the next milestone, very quickly after that, is a number of groups suggested use decoy state to detect the photon number splitting attack, if you like. So instead of brute force reducing your average photon numbers, what you can do is you can play tricks. You can make these decoy states and you can get statistics. And then from those statistics, you can figure out Eve's information. And that brought the slope back to -1, which is great. Now we have security and we can use practical sources, and we have a slope of -1, which seems to be, what we're stuck with, even with the ideal BB84. And the next milestone is from my point of view is in 2012, where my long-term collaborator, Professor Hui-Kwang Lo, and Vinci and Mark Curtis, Curti, they have these, they introduce measurement device independent QKD. And basically, instead of having Alice and Bob, Alice and Bob measure, we have a middle person that makes a bell measurement. And the really great contribution here is to say the measurement result now is no longer need to be secret. You can broadcast it because the measurement result tells you whether the two states are the same or they're different. It tells you the parity of the bit values sent by Alice and Bob, but only Alice and Bob knows the actual bits they sent, right? Everybody else just knows whether they're the same or they're the opposite. So that the contribution here is now you no longer need to have a trusted measurement, trusted person to make the measurement. The measurement can basically, results can be public. So it's a huge step towards just practice and towards a high security. Now, what about the key rate, right? Let's go back to this key rate. Well, even though the distance is being cut in half, but both photons have to arrive at Charlie, the middle person, for it to be measured. So we're not really gaining anything in terms of key rate and distance. So now we have the slope still back to, it's still -1, that's great, but much better security. Of course, there's some overhead, but the slope, the main thing is the slope is -1 and with better security. And then after that, it seems that we have sort of met a brick wall because there's people have looked at the fundamental bound of this key rate and saying, well, you can't beat this -1 slope. That's and you can calculate from information theory that this is what's limiting quantum key distribution, what's limiting the key rate and distance relationship. So it seems to be a brick wall, but shortly after, researchers from Toshima, Cambridge, Andrew Shields' group, they say, well, is it now? What if we do not require both photons from Alice and Bob to arrive? What if we do a first order interference? We just do an interference of the optical field, which an optical field is a square root of the intensity, a square root of photon numbers, which basically says that only one photon really needs to arrive at the measurement station. And that literally changed the whole relationship between key rate and distance, right? So now we're measuring optical field. We're not doing a photon-photon interference, it's optical field interference. It's like classical interference in optics. So that's what's the game changer is now the slope is -1/2. That means for at least for a longer distance or lower transmittance case, we can beat the prop bound, which is what's considered to be the fundamental repeaterless bound of key rate. So that's great. And even, considering practical detector efficiency and considering detector dark count, there's still a possibility of beating, of having a key rate higher than the repeaterless bound, the prop bound. So shortly after this proposal, literally less than a year, we have 4 groups in the world publish the results of a demonstration of twin field QKD. It's called twin field QKD because we're doing the field-field interference here. So this is the work that I highlighted. This is our work here. By the grad student, and she is Xiaoqing. She is co-supervised by my collaborator Huiquang Lo and myself, and this is a collaborative work in these 2 groups. I highlighted this because of our work and also because we use a very different configuration from the rest 3. So that comes from a theoretical that comes from a practical consideration of doing these very, very large long arm interferometers. So here's, let me show you the challenges. So the challenge is that if for a lot of you who has done any kind of interferometer in the lab, you know, even for small interferometers, it has to be very stable. Its stability is a major concern, and you know, let alone you have kilometers or hundreds of kilometers, that huge interferometer. So there's a huge amount of experimental challenge in stabilizing the phase for this interferometer to happen. And basically it involves, you have to have frequency locking between the two lasers of Alice and Bob. Ideally, to make it to stabilize, you need to balance interferometer. Otherwise, you have to have very, very low phase noise in your laser. If you have any sort of phase noise, then you cannot use unbalanced interferometer, which means Alice and Bob has to be exactly the same distance away from Charlie in the middle. And you have these hundreds of kilometers of fiber that you need to do phase compensation, because the two fields are going through different fibers. So those are huge challenges, and they're huge challenge even in the lab scale. Now becomes huge challenge when you're talking about very large distances. So that's why we use a very different approach here. Instead of doing a Mach-Zehnder type of interferometer, we use a Sagnac type of interferometer, where the two pulses, so one clockwise, one counterclockwise, they go through exactly the same fiber. So any phase disturbance for one pulse is going to be experienced by the other pulse, and that automatically guarantees a phase stability. And we use one laser that guarantees that the frequency is always the same, and so on. So basically, in our case, there's no need for frequency locking, no need for stabilization, and Alice and Bob does not have to have equal distance to Charlie. Because the interferometer is including in this entire rings. So in contrast, this is very different picture in this Mach-Zehnder type of configuration, where it's very difficult to allow asymmetric user location when you have laser phase noise. And because we can do this asymmetric locations, it makes making a network of twin field QKD possible. In a network, we can add more users here, and they all have different distances between the user and the central station, Charlie, that does the measurement. So this is the current status. These are two very new papers. The one is in Toshiba Group and one is USDC from China, and they are admittedly they are much better in terms of demonstrating the long distance and the performance. They are, well, in terms of the kind of resource they have and the kind of funding they have, they're also orders of magnitude higher than us. But my point is, they are using the Mach-Zehnder-based interferometers, which means they do have to have lots of resource, and that translates into cost in practice, right? They have to have lots of resource in doing frequency locking, in doing phase compensation, and they are limited to this symmetric setup. Alice and Bob, even though they are hundreds of kilometers apart, but the difference in the difference in length, in distance, in fiber length actually has to be, less than a kilometer, which is not exactly practical, right? So here are the three, recent work that we have done. So following the first demonstration of twin field QKD, we demonstrated, in fact, we can have asymmetric loss, and using an asymmetric intensities it actually has an advantage. And we also demonstrated recently the multi-user twin-field QKD network. And because of the time limitation, I won't go to the details of these. This is our first demonstration. I just want to show that in terms of overall loss versus key rate, we do have data points that breaks the prob bound, which is a good indication. And this is the asymmetric twin field QKD setup, where again we have demonstrated again with high loss situation with reasonable key rate that can beat the prob bound, and this is a network situation. So these are the few data points. This is my grad student Xiaoqing's work. She's worked at these asymmetric, very large asymmetry between Alice and Bob. Their difference in loss is more than is 15 dB, as high as 15 dB. And we could still beat the plot bound here. And with finite data, it's obviously lower, but still we are 30 times better than if you just trying to make an asymmetric case symmetric by padding fiber, right? That's never the preferable case. So these are the major results, and finally we have the results for the QKD network. Again, this is with 3 users, Alice, Bob, and David, and we've done each user pair separately, as you can see here. Now, the drawback is that can only be 1 pair of users communicating, but the network is quite flexible. You can have any 2 pairs communicating at a given time. So in conclusion, I wanted to say that we have demonstrated this autocompensating twin field QKD system with the Sagnac interferometer configuration. The major advantage is it really solves a lot of these practical issues, which can be done with lots of resource, but that also translates into higher cost. Whereas using this configuration, these requirements are either removed or reduced. And of course, we've demonstrated the twin field QKD. We have the actual key rates. And also, I'm really excited because I think we're the first and only group to demonstrate multi-user twin field QKD network. So going back to our initial goal, let's say, I think we have made a step towards QKD at a competitive cost over reasonable distances and with sufficiently high key rates. Of course, all of that, the key rates for twin field QKD is still quite low, right? But the rates times distance product is not low. And the twin field QKD also provides a high level of security in the sense that the measurement in the middle is independent, and it does not require security at the measurement part of the system. So I'd like to thank my collaborators, Huiquang Lo and Marcus Curdy. And Xiaoqing is really the major role that did all the experiments, set up the system here in my lab. And Mike Wang here, he used to be a PhD student of Huiquang's. He's working on the theory side on calculating the intensities. And then we have Reem is a PhD student working on improving our twin field QKD network. Finally, maybe I'd like to show a nicer picture taken in the summer, this past summer in Toronto. This is one of the rare occasions where we can have actually an in-person gathering outdoors in this tough times. So I will stop here. I'll be happy to answer some questions.
Thank you very much, Professor Jen. On the Q&A on the Hoover app, web app, we have one question, and we only have time for one question, so I'll ask you this. The question is, are there any technical drawbacks to using a Sagnac interferometer versus a Mach-Zehnder interferometer? Yeah.
Yes, very much. Thank you for the question. Would like to say, yes, there's the major issue that we have, because we have a bidirectional configuration. We suffer from Rayleigh backscattering, and backscattering get into the detector, and that, of course, if that can overwhelm the signal. However, so this is not an insurmountable challenge. There are multiple ways that we can deal with it. We can separate in time, so we can have the backscattering die out, and then we measure the signal. So right now we're looking at a burst scheme where we send out a signal. It's in a burst pulse train, and the backscattering will come back first, because it's the fiber. It's the first 20 kilometers of fiber that gives us the backscattering trouble, right? And then, but the signal is going to take a long time to come back to us. So we can use time division multiplexing, if you like, to get rid of the backscattering. And we can, of course, then you can say that the data rate will reduce because we burst. We're not constantly sending, but then we can make that up with wavelength division multiplexing. And especially in the network situation, right? We can have, this pair of user communicate at this time slot, and different pair of user communicate at different time slot. They're going to use different wavelengths anyway. And our ring network does allow both time division and wavelength division multiplexing in the system.
Well, thank you very much. There's at least one more question, but we don't have time but I encourage people to interact on the Quantum Days website for follow-up discussions. Thank you very much, Professor Jen.
Thank you. Thank you.
It is my pleasure to introduce our next speaker, Professor Claude Crépeau. Professor Crépeau is a professor of computer science at the McGill University. After his education and research in multiple countries, Canada, and then US and France, he returned to Montreal as an associate professor at Université de Montréal, and then later he joined McGill University in 1998 as an associate professor. He is one of his most perhaps well-known contributions is his work on the first paper on quantum teleportation. It's probably one of the most cited papers in this field. But today he'll be talking about relativistic zero-knowledge proofs. I am excited and looking forward to his talk. Professor Crépeau, please.
Thank you very much. It's a real pleasure to have this opportunity today. I want to thank the organizers. Now, today I want to tell you a short story and introduce you to an application that probably many people here are not familiar with. I want to consider the situation where you end up at a teller machine somewhere at the other end of the world, and you're trying to grab money from the teller machine. And in so doing, you push in your card, and then the teller machine asks you for your PIN number, and then you type it in. The transaction goes on, you get money out. But how do you know if the machine you interacted with is a real one or is a fake? How do you know you have not just given away this very secret information that enables you to access your money? How do you know that the next day, thousands of dollars will not be withdrawn from your bank account? Well, the thing is, you do not know. And the kind of protocol that I'm describing today is an alternative to this kind of application. The protocol that I will describe has two main characters that we call the prover, who corresponds to the person showing identification at the teller machine, and the verifier, who corresponds to the teller machine. And the question we're going to ask is, can we make the interaction between the prover and verifier so that at the end, if the verifier has been dishonest, he cannot convince a third party that we call the adjudicator that he obtained information that allows him to replicate what has just happened. So the prover corresponds to the user, the intermediary verifier corresponds to a fake teller machine, while the adjudicator would correspond to an actual real one. Now, the idea of what I'm going to show you today goes back to the 1980s by Goldwasser, Mikhail Rakov, and this is the idea of interactive proofs and so-called zero-knowledge proofs. What they introduce is an alternative to the traditional way of proving things in computer science or in mathematics, which is by providing a proof that the verifier can check on his own. It's interactive because a conversation actually takes place. So if the prover wants to prove that W is a member of a language L, he will prove that by exchanging information with the verifier on the right-hand side. And we want to achieve two properties to claim that this is an interactive proof. So we say that we have an interactive proof for this language if completeness is satisfied. That is, for any polynomially bounded verifier, there exists a verifier and there exists a prover, such that whenever the string W is in the language, the probability of the verifier accepting after talking with the prover is essentially 1. It's going to be 1 minus epsilon for some small epsilon. And we want to guarantee, so this is when W is in the language. When it's not in the language, we want to guarantee that that for the same verifier, whatever the prover does, whatever trick the prover may try to use to convince the verifier that W is in the language, he will not succeed, in the sense that upon a conversation about this W, the probability that the verifier accepts the string is going to be very small, below some small epsilon. Now, this property of soundness guarantees that the verifier will in the end believe that the string is in the language, and the membership of the string correspond to knowledge of the password. And so what the prover is actually demonstrating is the fact that he knows a classical proof that the verifier could actually verify. Now, the zero knowledge aspect corresponds to the fact that we wish that the verifier, whatever he obtains throughout such a proof, is useless, except for the fact of convincing him. So whatever the verifier does, we wish that the prover at the end of the interaction is convinced that the verifier is not able to convince a third party. Not only that he owns a classical proof of the membership of W and L, but moreover, that everything that has been exchanged could have been produced by the verifier without actually speaking with the prover. So this is how zero knowledge is defined. I will not go into the details more precisely of what zero knowledge is, but for today's talk, just think of zero knowledge as being not transferable. If the verifier repeats to a third party the conversation that he had with the prover, the third party will just say, okay, very nice, but I don't trust that this really happened. You could have made it up entirely yourself. So this is how we define the security for zero knowledge. Now, in the rest of this talk, I'm going to stick to a particular problem of computer science, which is the problem of tricolorability. Tricolorability of a map, or in this case of a drawing, is the question, given a map like that with 5 bird-shaped region, is it possible to associate one color to each region out of 3 colors so that any 2 neighboring regions are of different colors? So if you look at what's on the prover's mind, it's an actual tricoloring. If you check pairwise those regions that are neighboring each other, they always are of different colors. So this is an instance where the tricoloring problem is satisfied, and the prover would demonstrate his identity by demonstrating his ability, his knowledge of a tricoloring. Now, if we achieve that in zero knowledge, we will be able to do that in such a way that the prover will not, in the end, have learned a tricoloring at all. Now, the map tricoloring problem is a special case of a graph tricoloring problem, which corresponds here, where the regions correspond to the vertices and where the connections to neighbors correspond to the edges of the graph. But for this presentation, I'll stick to the map coloring problem. Now, moreover, I'm going to stick to this tiny example. In reality, we would be handling graphs that are very big to make this problem difficult, to make sure that demonstrating that this larger map is tricolorable is much harder than demonstrating that this small map is tricolorable. But for educational demonstration, I'm going to stick to this example. Now, in the classical proof, the prover would just give away the coloring to the verifier. But if the prover did that, then the verifier could run off and convince a third party that he has obtained a tricoloring, and he could fake being the prover. So that's precisely what we're trying to avoid, and that we will accomplish using zero knowledge. Now, in order to achieve zero knowledge in its strongest flavor, which is without computational assumptions, I'm going to revert to an alternative model known as the multi-prover interactive proof model, where you not only have one prover, but you actually have 2 or more provers. Now, this model also dates back to the 1980s by the work of Benor, Goldwasser, Killian, and Vigderson, where they introduced this model with the idea in mind that if you have a police interrogating criminals, they typically do that by separating them, so to assert truth more easily than when it's done separately. Now, in this case, we still wish that when the string W is in the language, that the verifier will accept probability nearly 1 after talking with the provers. And we still want that when the string is not in the language, that whatever the provers do, as long as they cannot communicate with each other, they will not be able to convince the verifier, except with a very small probability. Now, one question is, what is actually meant by they are not able to communicate? In the original work, this was not made explicit, although a few years later, Killian introduced the idea that one way of handling this would be by separating the provers by a distance, so that for some short amount of time, they're not able to communicate with each other. Now, notions of this type had been analyzed in physics in the 1960s, where John Bell introduced the notion of quantum non-locality and introduced the so-called local hidden variable model. So in this picture, you have a inner set of possibilities, which is the local hidden variable model, which is contained in quantum non-locality, meaning that quantum non-locality is more powerful than local hidden variable model. And all this is contained in a broader set of possibilities, which is signaling, where if the provers can signal, they will be able to break the soundness of the protocol. Now, by making some distance between them, we're able to restrict that they no longer are able to signal for a short amount of time. And then we have to decide whether we allow them local hidden variable model or quantum locality or more. Now, if we look at earlier work, if you combine the work of Bernard Goldwasser, Killian Wigderson with a protocol for tricolorability of Goldreich, Michali, Wigderson, this will not resist attacks from quantum provers. If provers are quantum, it's not proven that their protocol would resist that. And moreover, is it practical? Well, we'll see that indeed it's not very practical, because the distance between the provers in practical applications would have to be thousands of kilometers. Now, recent work by Chailloux-Leverrier showed an alternative solution based on Hamiltonian cycles, in which they were able to demonstrate quantum soundness. Now, as for practicality, it's still not achieved very well, because we're still talking of thousands of kilometers between the provers. And so the goal of our research was to bring this distance down to some practical distance. Now, the problem is that in previous protocols, the exchange in each communication that the provers and verifier had to do were polynomial in the parameter n that corresponds to the size of the graphs we're handling. While in our solution, we're able to do something similar in logarithmic communication. And achieving this in logarithmic communication allows us to bring this all down to a few meters. So our solution, these are my co-authors, our solution has been to go along the lines of Goldreich, Michali, Wigderson, but by restricting considerably how much of the colors are going to be transmitted in each round of the interaction. So our approach is the following. If I want to show that this map is tricolorable, if the provers at the bottom want to show at the verifiers at the top that this is tricolorable, they will answer questions from the verifier, where each verifier is allowed to ask for the color of a bird, of a pair of birds. So in this example, the birds number 2 and 3 are going to be disclosed, but they're not going to be disclosed in the clear. They're going to be disclosed in some encrypted form that we call a commitment to the color, which is given back to the verifier. And then at the other end, the other prover will be asked a similar question and will reply with a similar answer, but in such a property that if they both are asked for the same bird, then it will be possible for the verifiers to obtain the colors. Now, I'm not going to go into details of how we do the commitment, but basically the property that we accomplish is that by using special commitments of the multi-prover type, we're able to obtain a commitment such that when you commit to the same value in black on one side and in white on the other side, then you can actually tell what the color corresponding is. So our protocol is therefore just a two-prover protocol where each prover is asked for the color of two neighboring regions, and they answer in such a way that if they are asked the same region with the same black or white character, then consistency between their answers is checked. Now, however, if they are asked the same regions, two identical regions with different character, black or white, then the colors of the regions can be seen. So in this example, if you ask the same questions as before, the verifiers are able to check that the provers are consistent and that they give the same answer when asked the same region. But if they're asked the same region with a different black and white character, then the colors can be revealed. And then the verifiers can validate that indeed this pair was indeed well tricolored. Now, if you repeat this experiment a large number of times, you are able to convince the verifiers that indeed the graph is actually tricolorable. And as for the zero knowledge aspect, it's just a case analysis showing that whatever the verifiers do, they can learn either two colors or one color or no color at all, depending on how they ask their questions. So this guarantees the zero knowledge aspect. Now, let me briefly describe our experimental setup, because we actually demonstrated this in a laboratory in Geneva. We have a pair of prover verifiers sitting here on the table, and 60 meters further, we have another pair of prover verifier, and they communicate with each other with fiber optics to synchronize their operations, but they're sufficiently far from each other that we can ask questions and get answers back out from them in a short enough time that we can obtain their answers fast enough that they cannot communicate during the very short amount of time. Now, the verification process per distance is such that if you have the two verifiers with the nearby provers, the provers must answer their questions fast enough that a question starting from one verifier propagating towards the other verifier cannot actually arrive before the answer from the corresponding provers arrive. Now, if you move the provers further out, this is going to get more difficult to accomplish, but as long as you stay within the dashed gray area, the verifiers will still accept what the provers say. But as you move out of the gray area, then the answer comes too late. And we give up. Now, the interesting feature is that the verifiers don't need to locate where the provers are. They don't need to know where they are. All that they care about is that they answer fast enough to their queries. So this is sort of what our setup looked like. And we proved for graphs that had 588 nodes and 1,097 edges. And we set the parameter K for security to 100, meaning that all approximations and small epsilons are close to zero, exponentially small in K. Now, as for entangled provers, which I did not cover so far, it follows from a theorem of Kempe, Kobayashi, Matsumoto, Toner, Vidic, that if you change the protocol of two provers to three provers, you can actually achieve essentially the same security at the cost of adding a prover and at the cost of repeating more times. Now, how much more time is that? Well, what we were able to achieve in 1 second would be achieved in about K hours if you want to get an exponentially small amount in this epsilon. Now, just before closing, I want to cite a recent work by Chailloux and Barsamian, where they also implemented a similar protocol over the internet. Now with their new protocol, they were able to reduce their cubic previous work to n log n, which has made it much better, they claim. But it's you decide. We were able to run it in 60 meter, and they had to run it over 400 meters, even with this reduced approach. And so let me just conclude saying that we implemented our work with very basic equipment. And if we invest more on the equipment side, we believe we can reduce this to a meter and make it a practical implementation that can actually be used in reality. I thank you for your attention. It's been a pleasure to speaking here.
Thank you very much, Professor Capot. I don't see questions coming in. It might take a minute or two to post the questions on the Q&A, but I have one question for you. You mentioned the cost, the communication cost, and in your protocols, the order of log n. I assume that there's no protocol at the constant cost, and what does that imply if that happens? Like,
well, what it implies is that because the cost is logarithmic, we can we can also reduce the constant in the logarithm, and we can reduce it to distances that will be on the meter scale or even in the centimeter scales if we have enough short questions. Now, the drawback is that if you ask shorter questions, you have to repeat the protocol more times in order to achieve the same level of security. And this is where the compromise is. If we want to get very short distance, we have to repeat the protocol more times, especially in the quantum case.
Thank you very much for your talk and for answering the question. Please join me and thank Professor Capot again for this interesting talk.
Thank you very much.
With that, we transition to the third talk of the session by Professor Christophe Simon from University of Calgary. Professor Simon is a professor of physics at the University of Calgary and a faculty member at the Institute for Quantum Science and Technology. He is known for his work on components for quantum networks and quantum Ethernet in terms of quantum memories and light matter interfaces, and also his work towards development of theoretical development of quantum repeaters. Today, he will be talking about hardware architectures for the quantum Ethernet. So please join me and welcome Professor Simon. Christophe, please.
Thank you very much. Can you hear me okay? Yeah.
Yes.
Okay. Thank you. So yeah, it's a great pleasure to be talking here today. This is a picture of Calgary, you can see. And I can't advance. I have to figure that out.
You're not sharing your screen, Christophe.
Yeah, no, I'm trying to do it again because I couldn't move forward. We tried it out before, right? It's fine. Okay, very good. So I thought I should start with a brief definition of the quantum internet. So my tentative definition is that it is a large, ultimately global network that allows sharing of quantum information and of entanglement. Just to give you some idea what we are talking about. It would be, I think, good for many things. We heard about QKD, of course, and there's other cryptographic applications like blind quantum computing, private queries, secure data storage. There are quantum sensing type applications, for example, one could make better telescopes if they were entangled, or sort of other fundamental physics tests, measuring time more precisely, quantum clock networks. And then in the long run, I think many of us imagine that we would be able to network quantum computers, on large scales and create something that really is, maybe deserves the name of a quantum internet then. Now, the best approach, I think it's quite clear that the best approach for doing this, so for sending quantum information over long distances and for distributing entanglement over long distances, really depends on what distances we are talking about. So for moderate distances, it's probably best to just send the photons, directly. Then there are distance ranges where ground-based quantum repeaters, and I'll come to what a repeater is in a moment, but there are sort of fiber network-based approaches with some quantum nodes are probably the best way. But then I at least believe that at some point, for a certain range of distances beyond, a few thousand kilometers, we probably need satellites, and probably really we need actually a combination of satellites and the repeater principle, and I'll come to that a little bit later. So there's a lot of work to be done on these various technologies. So let me briefly explain, because it keeps coming up, right? Let me briefly explain the basic principle of quantum repeaters, and that's quite simple. So it's the idea is like if a distance is too large to really send your quantum information directly over that distance, because the photons will just get lost, let's say, then you can divide up that distance into a few pieces. You create entanglement in each piece individually, and you store it. So there's an aspect of needing to store things, needing quantum memories. And then once you have done that for neighboring links, then you use entanglement swapping, which is basically quantum teleportation, to extend the length of these links, and eventually to extend it to your entire distance that you want to cover. So this is the most simple kind of quantum repeater that exists. I should say that there are different types, of course, that have been developed now: qubits versus continuous variables, probabilistic versus deterministic, architectures that use quantum error correction versus ones that don't. I am here focusing on the sort of most basic and I think most near-term approaches, which are qubit-based and post-selection based. Okay, just this is for the experts. Now, in that category of even for those kinds of sort of simple, in quotation marks, quantum networks, there is many different technological approaches, and I would like to make one division here sort of explicitly, and I want to start with those approaches that are based on ensembles of atoms or atomic-like systems, as opposed to individual systems. I'll come to that in a little bit. So when we are working with ensembles, again, there's different kinds of ensembles. So there was this pioneering work in 2001 by these authors, Duan, Lukin, Sirac, and Zorda, who proposed an approach based on atomic vapors or atomic gases. Then a little bit later, at the time I was in Nicolas Gisin's group in Geneva, we started, and other people too, but these are our papers. We were among the people pioneering the use of solid state, just jumped by itself, solid state atomic ensembles, which had the benefit of having a very natural way of allowing multiplexing in frequency. So there was sort of a natural path towards implementing what we call highly multimode quantum memories, in particular this so-called atomic frequency comb memory that we proposed here. Then in the meantime, there has been a lot of work on these various approaches to ensemble-based memories. And so recently we thought that maybe the time had come to think about, the sort of do a comparison of different schemes and think about how promising it is to do near-term demonstrations, let's say over a distance of 100 kilometers, which in fact people are starting to do. So people are starting to do very, very basic, at least demonstrations of individual links of quantum repeaters. Nobody has really done an experiment like it is drawn here with 2 links. Well, maybe that's not quite fair, but let's say that these types of experiments are not very advanced yet. But in any case, here's a paper that we wrote about like how different types of repeater protocols would perform over like a notional distance of 100 kilometers, and what kind of sort of components they would require, what kind of performance they would require from their components. Here we focused on the memories in particular, right, which is a key element for the repeaters, as I explained, and 2 of the key sort of metrics are the efficiency of a memory and its lifetime. Sort of efficiency is like how efficiently with what probability are you going to get a photon back, after you store it in that memory, and then the lifetime is like how long can you keep it in that memory. So we have a pretty good understanding now of what is required to do these things. Another key element for at least some of the protocols is creation of entanglement, right? Obviously, if you want to distribute entanglement, you have to have a way to create it. And so I wanted to highlight a very recent paper that we have in collaboration with Pascal Snella's group in Paris, where we so they are like real world experts in making photon sources, single photon sources, and photon pair sources from based on quantum dots. And here we sort of came up with a way to create a bit of a new kind of entangled state, which is entanglement in photon number. So you either have so if there's sort of 2 separate modes, and you either have 0 photons in each mode or 1 photon in each mode, and it's an entangled state. So there's a coherent superposition of these 2, and yeah, so we are proud of this. That this is an experimental paper where it was shown that you can do that with a reasonable fidelity. Then so that was my short sort of section on quantum repeaters with atomic ensembles. As I said, there's also a lot of work on quantum repeaters or quantum networks with individual quantum systems. So not using groups of atoms to store light, but rather using individual atoms that maybe become entangled with a photon that they emit. Typically, it's done like that, and you can create entanglement in that way. And again, there is a lot of different sort of sub approaches. There are single neutral atoms in cavities. There's trapped ions. There's NV centers in diamond. We have worked on several of those in the past. More recently, in my group, we have been interested in single rare earth ions in solids. I didn't say that clearly before, but our work on quantum memories with ensembles was often, not always, but often for these kinds of systems, for rare earth ions in certain solids, because they have very good coherence properties, and they, in the ensemble case, they are very good for multiplexing. Like I said, you have a lot of different frequency channels that are accessible. Here, for the single rare earth ions, the multiplexing was maybe less an argument, but one thing that's attractive for a certain kind of these ions, which is erbium, is that they emit exactly at the ideal wavelength for long distance quantum communication at the telecom wavelength, around 1.5 microns. So that makes erbium a very interesting system. And then I also mentioned quantum dots. So quantum dots is a system where sort of photonics approaches are very advanced. People have have worked a lot on optimizing sort of the efficiency of the coupling between the quantum dots and the light. So that's interesting from a photonic perspective. And then if you have spins in quantum dots, and if you can maybe sort of electron spins, and if you can couple those to the nuclear spins that are naturally there, then that can be an attractive system for quantum repeaters too, because these nuclear spins are very good long-term memories in principle, and people are starting to do experiments on that. We are, because we are interested in these quantum repeater schemes, like we are developing sort of theoretical techniques to really analyze the performance of these various schemes. I gave an example before where we were focusing on the properties of the memories, rather than trying to quantify like exactly what kind of performance is required there. Here this is a paper where we focused on more like the properties of the photonic channels, one could maybe say, or the spin coherence for these individual quantum systems is also part of the things that we considered. So we are trying to make really realistic models, basically, of how these quantum networks would perform, and to enable us to make realistic predictions. Right? One of the goals that I think are important in this area, at least in the medium term, is to come up with approaches that can work at the room temperature. Like for now, almost the vast majority of approaches to these quantum network architectures requires either laser cooling or cryostats, often very low temperatures. It would be great if like eventually we could move away from that, right? It would make it much more scalable and would eventually, I think, reduce the cost of these things and make them more widely deployable. It's not easy to do this. The challenge is typically interactions with phonons at these higher temperatures, at least in solid state systems. But we have a number of approaches, either ultra small cavities to just speed up everything so you are faster than the phonons, or using optomechanical systems to interface between the spins and the photons and avoid these phonon modes that are detrimental. Because the spins themselves are actually quite good at room temperature. At least, for example, NV centers in diamond can have excellent coherence properties even at high temperatures. It's really the coupling to the photons that's the challenge, because of the phonons that come in. And a recent development in this context is that people have found at least one system in one material, which is hexagonal boron nitride, where this phonon coupling seems to be strongly suppressed, where the lines are somehow narrow, and that's really promising. But it's not well understood, and we are trying to help understand it, but we are not there, but we are working on that. So I think there's hope on this front. And okay, so this is a bit of a jump from room temperature back to really low temperatures. The reality right now is that many of the leading approaches to quantum computing are based on superconducting qubits. But there's high TC superconductors, so maybe one day people will develop that, right? But in the meantime, we are also thinking about how to interface these superconducting qubits with photons in view of networking them right over long distances, like I said at the beginning. And that requires these key elements that are called transducers, which will convert microwave photons, because so the superconducting qubits naturally like to talk to microwave photons, but then for long distances, we want to use optical photons for transmitting the quantum information. So we need to somehow translate the quantum information from the microwave language to the optical language, right? And this is something, sorry, somehow this keeps jumping on its own. So this is something that one can do with approaches that are similar to what we are using for quantum memories. It's in some sense a similar problem. So we have been working on that. So the same kinds of materials like rare earth ions, for example, erbium, seem promising for this task as well. Coming towards the end, so I said at the beginning that satellites are likely to be an important part of the quantum internet going forward. There is, of course, the famous Chinese MISIUS mission that has already shown entanglement distribution over 1,000 kilometers. There is a Canadian mission led by Thomas Yenevan from Waterloo that is expected to launch soon. And we are also developing a ground station for that in Calgary. And together with Thomas's group, we have been thinking about how these satellites could then be used, in sort of more general quantum internet architectures. And one possibility is to have sort of, again, repeaters, but where the individual links are made by satellites. And in this paper here, we showed that is actually seemingly a very promising approach to really going to global distances. If you really want to distribute entanglement between here and Australia or Europe or something, then that seems like a good approach. And you can use pretty simple low Earth orbit satellites if you have your quantum repeater stations on the ground, which of course then requires developing these these kinds of stations. In particular, one needs memories, quantum memories again, but also the ability to detect photons that are arriving from the satellite in a non-destructive way. But this is also something that people are working on. And another interesting solution is to have a really long-term memory on a satellite, let's say, in which case you could, instead of having a repeater, you could just have maybe a pair source and the long-term memory on the satellite, and you would send one photon down over, let's say Ottawa, and then the satellite would fly to Paris, let's say, and then you send it down there. But then you need a memory that can really have a very long lifetime. But this is something, again, that people are working on. And so an hour, for example, a 1 hour optical memory was recently demonstrated. And recently we wrote this white paper for NASA advocating, looking at memories on satellites, where again, there's already a BEC on the International Space Station, for example. So this is not as crazy as it maybe sounds, I think. So we are thinking about the future for sort of satellites and quantum satellites in the context of the quantum internet in Canada. There's a initiative funded by the Canadian government to develop a white paper and a roadmap for this area. And we are actually, so this is a project that is led by these three people here, including Thomas Yenevan, myself, and André Fougère from INO. And we are holding a workshop with key stakeholders in this area on next week. It's called KISA 2.0. Then finally, I just wanted to briefly mention something else that I'm really interested in, and that has a bit of overlap with what I was talking about, which is the idea that maybe there could be quantum networks in the brain. So that's, of course, more a quantum biology topic. But so the key idea here, there's two key ideas. So the one is that it seems that axons in the brain, so which are the little cables that connect our neurons, it seems that they can also serve as optical waveguides. This is something that we had proposed in 2016 and done a lot of modeling on, but there's starting to be really quite good experimental evidence that this is true. Here, this is the cross section of an axon, and you can see that the light is there, in this myelin sheath, like so sort of this little ring of light, right? Like this is what we had predicted in that paper. So maybe we have photonic channels available in the brain. And then on the other hand, we also have done a lot of work in the last couple of years on entanglement, small scale entanglement in the brain between spins. So there is all kinds of areas where these so-called radical pairs, entangled electron spins seem to play a role. So maybe we have sources of entanglement and photonic channels. So maybe maybe there's at least the ingredients for quantum networking in the brain too. And with that, I just wanted to put up my summary here. I think I won't maybe read it, but I'll flash back to it in a moment. And then I just wanted to thank my group members, collaborators, and funders in these various areas. And I'll just go back to my summary briefly here. Let's see, maybe we have time for one question.
Thank you, Christoph, for finishing on time, but we have time for a quick question. I don't see anything coming up on the Q&A, but in the meantime, I can ask one. As far as I'm, and this is my limited understanding of one of the challenges in the transduction, there's always this mismatch in terms of just the spatial distribution of the mode of the microwave in the microwave domain and the optical. Is that still a barrier in terms of efficiency in transduction, microwave to optical transduction?
I would say it's a consideration, but I think it's possible to design cavities that are sort of coinciding, microwave and photonic cavities, or at least to manage this issue. But it's something one should keep in mind for sure when designing these systems.
Thank you. I don't see questions coming up, and without a break, we have another session, panel discussion starting. And so please join me and thank all the speakers of this session. I hope that everyone got a flavor of how interdisciplinary quantum communication is. We had speakers from computer science, from physics, and from engineering discussing various aspects of this topic. So I would like to thank all the speakers again, and with that we can end this session.